Hi, everyone. Thanks for coming. So I hadn't actually really planned or prepared anything to talk today, but was having some really lovely discussions the last week and a half here at Lab Fortnite, and thought I would run through the IPVM quickly through the IPVM presentation I gave in Reykjavik in July, and then also a high level of the brain dump that I did into the project README for IPVM right before I got on a plane to fly here so I could have conversations with text. And then turn it into an open discussion. So I will just get started. So again, a lot of stuff has evolved post this presentation, but the basic picture is still there. So I've made 0 changes to this since Reykjavik. This is just to kind of give people a context dump. So we're talking about IPVM, which is the long-fabled execution layer inside of IPFS. The idea is to ship WebAssembly, at least to begin with, WebAssembly, fully deterministic computation into IPFS for a whole slew of use cases, including ripping out the concept of codecs completely and replacing them with WASM, having arbitrary compute, so you can pull down a WASM module, run it locally on some data you have, or push jobs to other machines, or even put a job up and say, hey, who wants to run this thing? So it is the long-fabled execution layer, or the easiest way to run WASM everywhere, or the fastest way to ship IPFS features to end users, or a step towards an interplanetary OS. So I'm going to talk about what, why, security, scheduling, a compute commons, and then have this open discussion, which may be a little spicy. I essentially just said most of this. So it's a blessed VM in every IPFS node. Also gives us things like the ability to upgrade parts of IPFS, force upgrade users, kind of like how a browser works these days, right? We don't ask them to update their browser, we just ship new stuff to them. Support features like autocodec, that's the let's rip the codec part out of IPFS and just make it part of the data directly, and then say, here's the WASM that I need to run next to the data, I will just run this over that, and that's how the gateway works now. Or anything else, right? I have Markdown, I want to turn it to HTML, I can do the rendering directly in IPFS, right? We should be able to do compute without consensus, or with consensus, but by default, no consensus. Do global adaptive optimization, I'll talk about that I think near the end, but this is applying a VM technique to essentially web scale compute and data, and do mobile, and in the 90s sense of mobile computing, where we can take some job, suspend it, move it somewhere else, and resume. This gets us everything that IPFS gets you for data, but for computation. Compute should be ubiquitous, right? The phone in your pocket is many orders of magnitude more powerful than a desktop PC in the 90s, right? The style of the lamp stack and having to extend it now with virtualization and all these other things comes from that model, and we don't live in that world anymore, right? So we should switch to, the argument is we should switch to this ubiquitous compute substrate. You should, as somebody shipping things into the IPFS ecosystem, be able to depend on, I have WASM around, and it is in the node, and I can just ship that to users and rely on IPFS. We should have deep integration with tooling by aligning on things like invocation spec, which we were just talking about. It should be fully consistent between clients. And we should replace things like Lambda with an open protocol. AWS doesn't have their own version of HTTP. They use the same HTTP, TCP, IP as everybody else. We should do the same thing for compute and storage. So requirements. For this use case, not for all compute use cases, it needs to be portable, deterministic, verifiable. I have question marks under these. These should now be exclamation points, pure and managed effects. So people often ask, well, I don't have network access, I don't have disk, I need to interact with the outside world, I need to be able to send an email after my job, all of those things. We actually have a model for this now that I'll talk about when I switch out of this and into the brain dump that I did in the writing. It needs to have enforced determination. So even if you have, obviously, general compute, because the halting problem could run forever. People like to say, well, we'll just narrow it down to the total subset of things that terminate. But if it terminates after the heat death of the universe, it doesn't matter, right? So we need to have some other mechanism. and rapidly, even after the first, within hours of giving this presentation previously, about 30 of us got pulled into a room and we just said, really simple, gas, because it's already baked into a bunch of WASM tooling. We should be able to move compute to data and data to compute, both directions, including push and pull, and also being able to say, hey, let's who wants to run this job for me? As soon as you do that, you need auth. So if you were around for the talk I gave yesterday, if you want to do compute, you need data, and to do data, you need, actually to do either of them really, you need some auth layer, and we're suggesting UCAN for remote invocation. Obviously, I'm biased, right? We originated UCAN inside of my company, but we've already seen people have success with this. So Web3 Storage has what they call bucket VM, which is essentially like a lightly programmable, think S3 bucket, and they're just using UCAN directly for that. That's for a really small subset of use cases, so hence invocation spec is a little bit broader than that. And effects. We're really used to doing side effects in everyday programming. That's obviously non-deterministic. So you can do just a pure data description of, hey, I would need to send an email to this person. Hey, runtime, I've just posted this as the output, so I've got pure data coming out, and also a description of things that I need run by the runtime. Not everybody will have access to all of the possible effects, like network access if you're offline, et cetera. But you can post that to the runtime, and it can hand that off to somebody who can run it. Or if you're totally offline and you need to run an email, it can suspend that until you have that capability. And that's effect systems I was just saying over lunch, or sort of like du jour in the programming languages and VMs community right now. Everything needs to be familiar, right? Major advantage of WASM, other than the fact that WASM is ending up all over the place, is that it supports all the LLVM languages. So you have 40, 50 languages out of the box that work immediately. We're not going to force people to write Rust or C or assembly script. Just, you want to write Ruby? Cool, done. And then adopt common patterns, manifests, crons, systemd, build packs. We're going to try to do something that looks and feels a lot like those so people can come and not have to learn an entire towering stack of things. We're going to do good developer-friendly tooling around this stuff. So lean to content addressing for everything. On the outside of a job, everything should be totally deterministic and fully described. Doing data flow, so DAGs, this is a well-understood method of invocation. We were just talking at lunch. You can absolutely do it to say like, hey, I need these things coming off of sources, but you can also, even though you don't know the output yet, say, relative to the output of this deterministic thing, in the same way that you can have a path inside of a CID. You can say, hey, whatever the output of that last thing was, because this is totally deterministic, lives under that CID, and we can just then do relative mapping inside of that. I think you saw this graph a couple times yesterday, privacy, verifiability, performance. I actually think that there's one more on here, but this is the basic idea. Anti-goals, I actually have written up now. So this is from the presentation. We had a discussion in Reykjavik. So execution is IPLD. You have a description of jobs. This is WebAssembly. That could also be Docker or something else for just the invocation spec. Then you have a tree of arguments, and then some other scheduling. This has actually since been kind of reworked a little bit so that we can cache the outputs of all of these. And then you have your output that points at that and says, hey, here's the results of that and some stats, et cetera, a system trace. We'll look at the updated version of this in a second. How you actually manage this, you have a stream of events. You're listening on some kind of a message bus. For totally pure things, it's really easy. You ask somebody, hey, could you run this job for me? And they do. If you need something off of a content address database, or relative to some mutable pointer, you first resolve that pointer. That's at the runtime level. It turns that into a CID and then pumps it into the system. But maybe you need, and that's now a pure computation, right? But maybe you need that to be an atomic action. So you're going to do, subtract $10 from Alice, add $10 to Bob. And then you go back and you look at the database after you're done, and you're like, oh, crap, it changed. So I can't write forward. I actually have to roll back and blow this thing up and run it again. Right? It's super classic software transactional memory, right? Because all of that is totally pure, we can do adaptive optimization. So as you're parallelizing jobs, there is a loss of efficiency, especially if you have a DAG rather than just a tree, because you have to do a little bit of coordination. This is Amdahl's law. It's actually much worse than that, though. This is the updated universal scaling law, which says that because you can have data contention, you're waiting for results from this one or for that one, all of these things, that as you add more parallelization, you don't necessarily get better performance. You often actually get worse performance. The flip side of this is if you're working on totally pure data, you never have to run that subjob again. You can just go into a giant table, look up the result, and plug that in. And the more people running jobs, the faster we can make the system for absolutely everybody. So this is the first demo that we're going to ship to people is, I ran this locally. These are actually totally separate jobs, but they have one component that's the same in the call graph. So we're just going to pull it down and make it 10 times faster on somebody else's machine. Caching intermediate results, even within a job. You can do this. A lot of systems do this per opcode for verification reasons. We think doing this between WASM modules makes sense, where we can tap them and store the intermediate results in IPFS. And then if I have some other job, I can now pipe that in to that job there and then continue on from that point. This looks a whole lot like a suspend resume system, which I mentioned earlier, which is actually also how Lurk works, if you're familiar with Lurk, where they externalize their internal state from time to time. The feedback loop here is we're going to fetch data, compute on that data, output more data, and then repeat. So we're going to make computed IPFS data the heaviest object in the universe. I mentioned earlier side effects. So if I need to send an email, send a tweet, read from something in AWS, we can still do that, but not every node will be able to execute it. So if I need to send email as somebody or as a company, I have to do service discovery. Who has the ability to do this, right? So as the output of one job, let's say it's like, and you also need to send an email. Great. Who's able to send an email as this person? I get a lock on that job, because I don't want to send 10 emails, I want to send one. Get a lock on that job, hand it off to them and say, hey, please run this for me. They go and they do the thing in the real world, and then they come back and say, hey, here was the result of the transaction, and we've turned it again into, as far as this base stream is concerned, pure data. So if somebody's playing over this stream to do verification, we trust, and it's signed, right, that this trusted thing that happened in the real world actually happened, and that this was the result. Talked a little bit about contrasting IPFS itself. Security. So there's two models that we need to do this in production. One is SPKI, Simple Public Key Infrastructure, or SPOOKY, which is what UCAN is. That's the good-looking bird down there. And object capabilities, full-blown OCAP, which like CapDP or the latest spec that's getting worked on for this is called OCAPN, like OCAPN, my captain. The difference between the two is in SPOOKY, something like UCAN, it is extremely fast, it's immediate, you just present the credential and it runs, but it is, revocation is slower and eventually consistent. And you don't know who's subdelegated. You don't have a central place to look at that. In full-blown object capabilities, it works essentially by a series of proxies. If you want to hear more about exactly how, we can talk through it later. That means that I have to now bounce between, because each of those proxies live in a particular place, I have to now bounce between them. And if I'm going back and forth across the planet, there's a performance cost there. But if you're doing HIPAA compliant stuff, this is actually a really, really nice model. It is, in fact, fully general capabilities. It, in terms of security, blows access control lists like completely away. It's amazing, but it does have this liveness requirement. You have to be online. It's not partition tolerant. And it's a little bit slower than something like SPOOKY, but they have this trade-off. So we need to be able to support both, and in fact, you can get them to talk to each other. The more capabilities you have, send email, read from the internet, network access, disk, all of these things, the more capabilities you add to your invocation, the fewer nodes will be able to actually run it. So you should keep that as thin as possible. In fact, frame your computation in the most pure way possible will mean that it's faster, more optimizable, reproducible, et cetera. we need to do payment with state channels is what we think is the best way to do this, because you can do point-to-point payment without having to go through a blockchain and incur that payment time delay. You can do this directly with UCAN. So we're actually, we've seen somebody do this in the wild. So like, we should just write down for everybody else how that works. We're calling it UCAN channels or UCAN-chan. You essentially do a matchmaking DHT. I would like to run this job. Here's how much I'm willing to pay for it on this much gas, or this many steps of WASM execution. And then if I want to talk to, I'm in this top left, and I want to talk to the system on the bottom right, I can go through one of my collaborators on the payment channel network. And if there's services that need to get run between these, they can delegate to each other both a subjob and payment in that network. So where to actually start? Ship WASM into an IPFS implementation, manual invocation from CLI, interplanetary linked invocation format is what we were calling it. People seem to really hate this name, so we're probably going to change that. Concurrent distributed job scheduler, sensible defaults that are overridable. So this will be convention over configuration. Experiment with deeper integration with WASM IPLD and similar, cron jobs, event triggers, et cetera. And then eventually do push jobs to a particular address, but that is not the core goal. So then I asked people to disagree with me in Reykjavik. They basically didn't. Yeah, so that was that one. Let me pull up really quickly so we can then get into the conversation, and then yeah, there we go. So right before flying here last week, I figured I probably needed to do a bit of a brain dump so that I could even have conversations with people about this stuff. So this was like really stream of consciousness, at the airport, writing things down, making diagrams. Ooh, that's, yeah, okay, like that. People get really confused. What's the difference between IPVM, WASM IPFS, and autocodec? I covered a little bit of that earlier. WASM IPFS is an existing project to replace big chunks of IPFS with WASM. Autocodec is replacing the built-in codecs with being able to do that dynamically at runtime. And IPVM is really what I just talked about. There's a bunch of writing here, but the interesting part, I think, is this. So this is high level on a invocation spec where each invocation, in this case, it's WASM. We only care about WASM, but we are going to open that up because between IPVM, Bacalhau, WarpForge, BucketVM, FVM, I feel like I'm missing one. We all have something that looks kind of similar, and so we should just do one, right? So that WASM part could then become generalized. We need this separated out, job versus config, where config is information for cron, or links out to other part of a call graph, or all these other things. We need the invocation part to be like this, so that I can cache the output of just the computation without information about how it runs separate. Because I want to be able to reuse the output of this deterministic computation. The result is this stuff here in red. So we'll have a result of just the invocation that you can look up in a giant hash table, and then information from this session of I ran this, and this was the output. It points at the job and the job config and the trace, and any other information that I would need there. And then this purple stuff, so up here you'll see in the result, it has pure output, which is like, the 1 + 1 is 2. Also, please send an email and kick off another job. So 2 things to note. One, yes, we can have a upfront DAG that says, please run all of this stuff. That's really excellent to have, because now we can do really smart things with how we schedule the different parts of this and decide, I want to run these actually in parallel or in sequence. We know that all that matters is the data dependencies, right? This is called Church-Rosser theorem, right? So how you want to move that around doesn't matter, right? But in the general case, you also want to be able to choose run this or not, depending on the inputs I got. So we also need an effect that is, hey, on cue, this other graph to call as well. The runtime, so there's a separation here, which is why this is a dotted line. The runtime sees that and then goes and does other things. Send an email, create a new job, etc. There's a whole bunch more writing in here about payment, and you saw the managed effects stuff and whatnot. Some projects that we're hoping to learn from. Oh yeah, IPFS fan as well, which is an existing project from a couple years ago. If you haven't seen the PACT/Hydrologic or Bloom stuff out of Berkeley Orders of Magnitude, it's fantastic. They did this paper late last year called New Directions for Cloud Computing, which describes, 85% of what I just presented. I only saw this paper 2 weeks ago. I'm like, people are already working on this stuff. Amazing. If you can frame stuff in Bloom or Hydrologic, you get like massive improvements in performance. It's fantastic. Nix also does a bunch of things like this. And they have input addressing, which is basically what we're talking about. But they have an experiment for content addressing as well. So we should talk to that community and say, like, hey, do you guys want to use this stuff too? You're not even in the IPFS world, but we think that we're doing some similar stuff, right? So we should learn from them and feed it back into the system. Kind of our roadmap is we're currently in a learning phase where we're hacking stuff together with bash scripts and Node before doing this all in Rust. Memoization table, module pipelining, that's the DAG stuff. There's a lot of questions about what the ABI should be on the WASM module. I assume it's going to end up with C calling conventions. We'll see. We have to actually ship something for people to argue with. Pure effects, so we're not going to do email today. We're going to do read from a mutable pointer on IPNS or DNS link and see if it's updated and do all the atomics. And then with a demo of the adaptive optimization stuff I talked about earlier. A bunch of specs that we think we're going to need sort of out of the gate. I've been really itching to write basically all of these and a few others while I've been here, but I've been in continuous meetings and presentations. So hopefully soon, maybe I'll do a bunch of writing on the plane tomorrow. And then a fact. So that's the presentation portion. I would love to take questions. Or actually, let me rephrase that. I would love to open this up to discussion. Great.
What's IPLI? As in, what's the I?
Interplanetary Linked Invocation.
I thought so. And is it an IPLD document that describes how to execute a job? As in, it's essentially a standard spec for describing the stuff?
Yeah, it is. So IPLI is in pictures, is this blue one here.
Awesome.
Yeah, and then we're calling this a session for the rest of it. I've been warned not to pollute the IP, like the interplanetary namespace, with too much stuff. So we may need to rename some of this stuff. Also, for whatever reason, I've had some people are like, yeah, IPLI, whatever, cool. Some people hate it with the burning passion of 1,000 suns, and I don't know why, but we're going to just change the name. So.
Well, it sounds to me like IPLI is what we should collaborate on and Bacala should adopt. So that's my thought.
Yeah.
It has a name now.
Yeah, so I've had a couple conversations in the last few days, and in fact, the original idea was we should, if this is general enough that it can serve other people's use cases, let's absolutely just make it work for everybody, right? And then all of our tooling works together. The other thing I want to mention about IPVM in particular, we have this effect system, right? Our use case is sub-second invocation on deterministic outputs, but people will absolutely want to do video transcoding or machine learning, which is non-deterministic. That sounds like a great fit for the effect system, where an effect could be, run this thing in Bacalhau and give me the input back, the output back. So I want to tie all of these systems, Fluence, Bacalhau, Bucket VM, all of these things together with that effect system. It's sort of roughly how I'm thinking about it.
No, it makes total sense. And so an effect is a bit like an event where another system will see that event. The emission of the event is deterministic, and the other system will go, that means I now have some instructions to go off and do my thing with.
Yep, exactly.
Awesome. Okay. That wasn't even a question. That was just me understanding.
Yeah. The other thing, so relative to the call graph that we were talking about before, when you start mixing call graphs, pure call graphs, and trying to do optimization on that with effectful things, it can get kind of hairy. Thinking about it as data flow, which it is for our case, right? we've been doing a lot of stuff with differential data flow inside of Fission recently for a database that we're working on. If, as part of the input spec, you say, here's my, I guess part of the job spec, rather. Here's the pure stuff, and also I have some impure things that I need to grab from an external system. As soon as you have that input port, you know that you're waiting for something, right? And so that gives you the idea for the scheduler to say, okay, this needs to be delayed until this other thing is done, and I can determine between when it gets kicked off and when I need it back in, where in there I should schedule it. Should I push them all off as late as possible and then run them all together, right?
Yep.
In case there's failure in here, or should I run it as fast as possible, right?
Yeah, that's interesting scheduler decisions to be made there.
Yes, yeah.
Hey, for deterministic compute, is the idea to just trust locally that the compute that you did before was the result that you're getting back? And are there ideas on also using ZK proofs to actually send that as a result if someone is like invoking that we're outside of the trust model?
Yeah, so how do you do verification? If you're running stuff yourself, which one major use case we see for IPVM is I'm in a browser offline on a plane. I should be able to run it totally locally and not trust anybody because I trust myself, right? If we look at Wan's triangle, verifiability has a trade-off on performance always, right? Same thing with privacy. We can talk about privacy totally separately. That's a whole other discussion. Along the bottom here is essentially fully trusted. So maybe even I have a credits that I'm going to put in, a payment channel with a service provider, and I will only have them pick up my jobs, right? I don't have to do, I have an SLA, I don't have to worry about verification. If I'm going to put this into the general network, I now have two modes, optimistic verification or ZKPs. ZKPs work immediately because if you can bake those down into WASM or have a execution that is, say, built on top of Lurk or something, right? But that is slower because it's ZKPs, right? Optimistic verification plus ZKPs, I think, is a really nice model. You can run it twice, or however, whatever replicating factor you want. If they disagree, you find where they disagreed, and you run that in a snark-based WASM engine. That's slower, and then you slash who did the bad computation. So your verifier now is a snark. So that's one model, right? So we still have to do a lot of actual, hands-on stuff with this, but that's one theory for it.
I have a specific sort of concrete suggestion about how we start to standardize on the invocation spec, while keeping things flexible, to Simon's earlier point about wanting to be able to keep iterating on it as well.
Yeah.
And that is to kind of pin down, and I think we already talked about this a bit, to pin down the outer part of the spec more than the inputs and the outputs maybe, but the actual part about how you execute the WASM or whatever the other payload is, the program, could have different keys, and those keys could be broadly, for one thing, we could maybe version them. So we could have wasm.v1, or we could have your domain name backwards -wasm or something and then we can iterate on that inner piece while the outer piece is already more stabilized, and kind of stabilize it over time together as we go forwards. It's just a suggestion.
Yeah, I fully agree.
Yeah. Absolutely
agree. So something that we've learned a lot in UCAN is there's all of this writing, right, which is a general spooky shell, basically. And then we have capabilities which are completely undefined. We're going to ship a standard library, but it's not going to be inside the spec. So what a spec has, a working model in this community that we found works really well, is to say, here is the minimum number of things that we need to agree on so that we're interoperable. And please fill that with whatever you need. We're going to add fields so that things are extensible, like this here, extension. And if you and some other team need to do extra fields that nobody else understands, that's great. There's nothing in the spec that says that you can't do that. Just don't expect to be interoperable with everybody else on the open network. But if you're running this inside of a data center or with a particular collaborator, like, go for it. We need to iterate quickly, learn, change this stuff, et cetera. Absolutely. And I think that there will be, like, even if we go back here, right, what's ended up happening inside of UCAN is there's all of these specs that have popped up around it that say, how do we extend the spec for certain use cases? If you implement any of these other specs, don't expect them to be interoperable with everybody using UCAN. But if you're using Awake, everybody else who's using Awake, you should be interoperable with, right? So I think following a similar model, like, this is just us learning about how to do stuff, like, in the commons, right? Fully agree. Yeah. The other thing I should mention too, we were running monthly calls for IPVM in particular. That doesn't have to be the space where we do an invocation spec. Maybe we do that on a COD regular call or something. But if anybody's interested, we're running the call on Tuesday. If you go to luma/IPVM, you can sign up for the calls. And I'm going to be super jet lagged, so this will be awesome.
If you have multiple workloads that need to be run on the same host, and we are using UCANs to, like, transfer some data around, how do you envision, like, the triggering of, like, every next job to happen? So, for example, if I have a requirement that is coming from the previous job, I have some output, I need to push that. So basically, I'm probably going to pass a CID around. How would the second job be triggered, and where that needs to be done?
Right. So you describe a call in the simple case. You describe a call graph that says essentially think like Unix pipes. The output of this is going to go into the input of that, and because it is a single graph, you know exactly the shape of data you should get out of one that'll then go into the other. Right. The downside of this is that you're externalizing some state in between. So we need that in order to content address it and store it for later. There's a bit of work happening in the actually in the databases community for doing distributed queries that says, well, what if I have one query in SQL, another in data logging, all these things? What if you could bake that down into some common format that we know about, so we don't have to do serialization in between, and then we can just weld these together, right? So there's some stuff happening there. So that's actually relatively. Not the IR welding part, but like how do I get data from one into the other is actually relatively straightforward. The harder one is if I have to spark a new job and say, hey, I'm going to start this whole other thing that's not in the main call graph. You're essentially going back to the top again and saying, okay, well, my inputs need to look like this, and you're back at square one. In theory, because this is all started from the first job, you know the shape of the data. Essentially, you know the types. In terms of IPVM and WASM inputs, we're looking at the component model spec, which includes the WASM interface types, to stick those on the outside, basically.
Hello, I've got some questions about effects.
Yeah.
In the current thinking, are they things you have to declare up front, or are they things that you can decide to do as part of execution? I mean, I suppose the obvious one is like, maybe I want to send an email, maybe I don't. The less obvious one is maybe I've got one job, which is going to look at a photo, do object detection, and then I'm going to do like sharded machine learning across all of the objects it detects. And actually, I don't know how many shards I want until I've done that first job.
Yeah, so it is, exactly that. If you have a graph that's ahead of time, you can do really smart things in the scheduler, but it's not general enough for all cases, right? So if I have to do some computation to understand how many jobs I'm actually going to need and say the level of parallelism, then yeah, absolutely, that has to go through the effects system. And your output will say pure output, or status code 0 because it was successful, pure output, hello world, effects, and then this just list of effects, which are in themselves more call graphs. Yeah.
Cool. Can I ask another question? You mentioned something about effects being signed in their response. So it's a way to introduce non-determinism or impureness into this pure world. how does that work, basically? Because it'd be good to know, like, how we can use those signed information, those signed messages to verify, basically.
Right. So there's two levels of effect, right? One is inside of the IPFS world with content address data, or say reading off of a blockchain, something like that. I can produce a proof that says this actually happened. A thing that we're playing around with currently for a different project is things like DKIM, which is a way to sign with your email provider. So like with Google, to prove that you control, essentially you send a message with a challenge in the subject, and then that gets signed by Google to be like, yeah, no, totally, this was done by the person who controls this email address, right? And I can be like, hey, you can find me at this email address on IPFS. Amazing, right? But you have to trust Google's signing authority, right? Or you pull down a tweet off of the internet, and you use the TLS negotiation secrets to prove that it was signed by Twitter's CA with DNSSEC, right? At the end of the day, you have to trust something in there. In the general case where somebody's signing things, and it's just like it's another node, right? That's running it. This gives you the ability to slash them later or something, right? It's just a way of verifying that, like, yeah, they said they were going to run this thing. They did run this thing. This is what they attest to. They could totally lie to you, right? Yeah.
Is there any support for protecting against attacks of, like, doing something that I shouldn't have done? So if I send an email with some sensitive data in it, I'm not going to tell you that I did that because, well, I'm trying to exfiltrate secrets from your network. But the service knows, but maybe the runtime doesn't know to ask the service whether or not that happened or something like that.
Right. So in the capabilities model, you would have a UCAN that says you're allowed to send the output of this computation with my email to this address, let's say. And you can scope that down as granular as you want. Now, if you give it like super user rights to everything, then like, yeah, it can do literally whatever it wants, right? But yeah, so one way of thinking about that as a model is all capabilities models are proactive rather than reactive auth. And so you really follow the principle of least authority and say, like, we're just going to give you access to this and nothing else.
Thank you very much.
Thank you.